All right, everybody. Hello. So start for another week. I graded the exams. We're good to go now. One thing about the exams, I didn't include Poisson and binomial in this exam. They'll be in the final, just to let you know. So please keep that in mind. Don't forget that stuff. All right, today we're going to talk about correlations and regression analysis with correlations. We're going to talk about two different kinds, the Pearson correlation and the Spearman correlation. So let's start with the Pearson. But all correlations allow us to judge how strongly two variables are related to one another. So they're called bivariate correlations. With the Pearson correlation, the assumption is that each variable is continuous, quantitative if you prefer, interval ratio if you prefer, but it's a continuous random. Each variable is continuous. We assume that individuals are a random sample of the population. The relation between the two variables is linear, so it's not a curve or anything like a cubic form or quadratic or anything like that, and that the two variables are normally distributed. So that's a Pearson correlation. At times, the Pearson correlation isn't the best possible correlation. In that case, we can use alternative types. These are known as non-parametric statistics, and we'll talk about non-parametrics in a separate chapter at the, we're getting close to the end of the course, so coming up soon, we'll talk about non-parametric statistics. Non-parametrics are statistics that don't rely on a known distribution. So generally, when we talk about a known distribution, we're talking about the normal distribution. So let's look at the assumptions of the Spearman correlation, like when you just don't meet those, the normality assumption in particular. Data must be ordinal or continuous, right? So remember, ordinal is an ordering. There's a monotonic relation between the variables, between the different variables, between the data, the variables. So they're not linear. So here's an example of what a monotonic relation would look like. So the red is a cubic. Cubic, you have change in direction. So you're going down, you go up and down again. So that's a change in direction. So this is something that most correlations are not good at dealing with. Monotonic, though, see, this is nonlinear. So a line would be just a straight line. This is nonlinear, but you have continuing decline in this continuing decline, although the slope changes a little bit. So it's steeper right here, it's less steep, and then it's steeper again, right? So, and then less steep, but it's still going down. There's no change in direction. So that's monotonic. Regarding correlations, all correlations range from 0 to plus or minus 1. The absolute value represents the strength of the relation, and the sign, whether it's positive or negative, represents the direction of the relation. So correlations can, well, here's a visual of a correlation. So a visual of a correlation. So I actually like using this visual because it does two things. It shows you strength and direction. Remember, strength is the absolute value, direction is the sign. So here's an example of a perfect positive correlation. When you have a perfect correlation, all the points, so these points represent like the meeting, the intersection of two different variables. Say that we have one variable on the y-axis and one on the x-axis. Like say we have self-esteem and happiness or something like that. So self-esteem is on the y-axis, that's the vertical axis, and the x-axis is happiness. So for each individual have a score on two variables. So if, say I was conducting a study looking at self-esteem and happiness, whether they're related, and each person would complete a measure of self-esteem and then a measure of happiness. I'd get their score in each, and where their scores meet, that's what these points represent. So these points are it's the intersection of their two scores. When we have a positive correlation, those points make a straight line. You'll see that there's a little line running underneath that. That line minimizes the distance between the point and the line. So these points are perfectly on the line, and you'll notice that the correlation is 1. So it's perfect correlation, because again, correlation can be as high as 1 or as low as -1. And let's see, the sign is positive. So because it's positive, we're sloping from left to right, down to up. With a perfect negative correlation, we're sloping from left to right, up to down, right? That's a negative slope. And this is a -1. So this is a perfect correlation. So again, the strand, you ignore the sign. So these are perfect correlations, but the sign tells us whether it's going up, it's positive, or whether it's going down from left to right, it's negative. In this example here, we have a strong positive correlation, but it's not perfect. So it's 0.9. So you notice now that this is called a scatter plot, that the dots are scattered a little bit more so than they were in the perfect correlation. Yet if we were to draw a line in this clustering of data, we'd still see it's linear, right? It's not curvilinear, but there's just more scattering around that perfect line. Here we have the opposite, right? The reflection. This is a -0.9, but it's going down from left to right. This is going up from left to right. The negative is going down from left to right. And this is a weaker correlation, still not bad. It's 0.2, 0.5, right? But now you'll see there's greater dispersion of these dots around that invisible straight line. And then here it's the negative reflection of the 0.5 positive correlation, okay? And it's going downwards from left to right. So that should give you a good visual. I mean, you can get a lot more scattered than that. Generally, it's rarely ever this perfect. So when we measure the relation between two variables, we have two options. One is the covariance and one is the correlation. In order to calculate the correlation, we start with a covariance, right? Covariance. Just like we had for the variance equation, we have a shortcut equation for calculating the covariance and then therefore the correlation. But just so that I jump from covariance and I have correlation in the middle and I go to a shortcut for correlation. So let me explain how we got here. So this is your covariance. So if you look at this equation, it's just like the variance. Remember, the variance was sum of x sub I minus the mean squared over n minus 1. The only difference here is that we're not squaring, we're multiplying two different variables, x and y. So if we just converted if we let y equals x, we'd actually have the variance again. The variance would be xi minus mean times xi minus mean. That's why we squared in the first place, right? But now we're looking at the relation between two different variables. By not squaring it, we open the possibility of a negative value. Remember, in the variance, we squared this, so we'd eliminate the negative values. We wouldn't get a 0 up top. But here we allow for negative variables. The correlation is a standardized covariance. We've talked about standardization before when we were looking at percentiles and z-values. That's the way to standardize a variable. Well, here we're standardizing the covariance by dividing the covariance by the standard deviation of each variable. Please remember this, because this will come in handy, especially in exams. R is a symbol we use for a correlation, and this is for a Pearson correlation. And Spearman, I'm not going to have you calculate that, but if you ever are using a computer, you know that they have different options. The shortcut equation for the correlation is a lot like the shortcut equation for the variance. If you remember this, that was sum of x squared times sum of x squared over n, and then this was n minus 1 at the bottom. So this is basically the same thing. The only thing is here we're also adding the standard deviations. So these are the variance equations, right, that we had from the numerator of our variance or shortcut variance formula. So we're basically doing the same thing again, except for x squared, we have two variables here, so x and y. You're going to use this to calculate the variance if I give you a problem covariance if I give you a problem involving the covariance. The correlation itself is a measure of effect, where a small correlation is less than or equal to 0.10, a moderate is less than or equal to 0.03, greater than 0.1, but less than or equal to 0.3, and then from 0.3 to 0.5, you have a large correlation, or excuse me, above 0.5. So I'm sorry, 0.1 to 0.3 is a small, 0.3 to 0.5 is medium, and greater than 0.5 is a large correlation. Excuse me, I had that wrong. I mean, anything below 0.1 is extremely small. So we consider those heuristics for what's considered an effect, the relation between among those variables. So it's coefficient. So the correlation is an effect size. The coefficient of determination is another way to communicate the effect. This looks at how much variance is shared between two variables. The greater the amount of variance shared between the two variables, the greater the effect, or the greater the relation between the two variables. The coefficient of determination is merely the R squared. You just square it. The R squared works with the Pearson correlation. It doesn't work so well when we use non-parametric data. When we have not non-parametric statistics, or when we have non-normally distributed non-continuous variables. Let's look at we're not doing this here, so you don't have to worry about that. So I'm going to erase that. All right, partial correlations. So when we just correlate two variables, that's known as a zero order correlation. Often, though, we need to control for the effects of competing causes. This is what we call the third variable problem. Third variable is a confounding variable. A confounding variable is a variable that's related to the other two variables. I often give the example of ice cream and murder. Did you know ice cream consumption is related to murder? Does that mean that eating ice cream makes one want to commit murder, or that committing murder makes one want to eat ice cream? Well, no, it's just that the two of them are correlated. And the reason they're correlated is because of seasonality. People tend to eat more ice cream in the summer, and people tend to sadly commit murder more so in the summer than in the winter. So that those two variables are related, but they're related because of a third variable, season. That's what we call a confounding variable. So we often like to eliminate the effect of the confounding variable. So by doing that, we can get a better, clearer relation between the two variables. And the equation for doing a partial correlation, in this case, we're correlating A and B, these two variables. These are just generic terms, A and B. And we're eliminating the effect of variable C. So C is our confounding variable. So the correlation, so if you look at this, it kind of speaks for itself. We're looking at the correlation between variable A and B, and we're removing the relation between A and C and B and C, right? So the R, A, B, so that's correlation between R, is a Pearson correlation, right, between A and B. And then we divide the numerator by the square root of, basically it's R squared, right? Because R squared, so we have 1 minus the R squared relation between the two variables. So this is the proportion of the variance not accounted for or not shared by the two variables. So using the correlation matrix below, calculate by hand the partial correlation for depression and self-esteem controlling for perceived physical appearance. This is a prototypical correlation matrix that you'd see in any paper or maybe in the textbook. So a correlation matrix is symmetrical, and there's like an X, like a diagonal of zeros here. Well, actually, no, this is not. Yeah, I should say there's a diagonal of ones. This correlation matrix is a little busy because there's a lot of things in here, but generally you have the correlations and nothing else, and then your diagonal is all ones. Correlations are standardized values, so this represents the variance of each variable. However, you could also interpret it as a correlation with itself. Like, for instance, the correlation between this variable called summated CESD score, and that's a measure of depression, right? depression, when we do a lot of research, we use the Center for Epidemiological Studies Depression Inventory, CESD, but there's other inventories as well. But in this case, the correlation between CESD and itself is 1. The way we read this is we look for the intersection of the variables. So depression, and every variable on the y-axis is also up here in the x-axis. So you have a column for depression, a column for self-esteem, and a column for perceived physical appearance, and that's matched by a row for each of those variables. Okay. So if we look at the first cell here, or first like box. So again, this is an output from a computer, and there's more than you normally would get with the correlation matrix. But we have depression correlated with itself. It's 1. It's perfect because it's the same variable. But if we look at depression, its correlation with self-esteem is negative 0.692. So that's a strong correlation. Remember, the heuristic was greater than 0.5 is strong. And remember, when we're looking at strength, we ignore the negative sign. But it is negative, meaning that the higher the depression, the lower the self-esteem. The higher the self-esteem, the lower the depression. These other values here, just for your information, this is a p-value, looking at the probability of a value this extreme or more extreme. It's 0.000. That means it's less than 0.0001, right? And this degrees of freedom essentially represent the sample size. So it's a pretty big sample size. I think there were 386 or 387 individuals. Okay, so that's what we're looking at here. So you see, this is your prototypical correlation matrix. So let's go ahead and do this. And I did this by hand here last year. So we use the shortcut equation. So it's R, the correlation equals the summation of the product of x times y minus the sum of x times the sum of y divided by n. And this is divided by the square root of each of the, basically the variances of each variable. So it's giving you the standard deviations. The reason you don't see the n minus ones is here because they canceled out, right? If you remember this equation for a variance was divided by n minus 1, and same with the covariance, but here we cancel them out because of what we have from these standard deviations. So that's the same as the covariance of x times y divided by the standard deviations, and again, those denominators cancel out. So we need certain values here. So what do we have? So what do we have? What did I actually am looking at the wrong thing. Am I looking at the wrong thing? Yes, I'm looking at partial correlation. Here it is. I'm sorry. Yeah, let me go down here. This is what I'm looking for. My mistake. The partial correlation here was R, A, B. So we'll let A equal depression and B equal self-esteem and C equals perceived physical appearance. So we need the correlation between depression and self-esteem, and we saw that was minus 0.692. Okay, and then we have where am I? Here we go. And then we have the correlation between depression and perceived physical appearance, and the correlation between self-esteem and perceived physical appearance. We need depression and perceived physical appearance minus 0.446. There it is, minus 0.446. And then the correlation between self-esteem and perceived physical appearance was pretty high, 0.590. So we have to subtract here, right? We're subtracting, but one of these is negative. So you have a negative times a positive will be a negative. So basically we're adding these two together, right? We're adding here instead of subtracting, right? Because this becomes, the negative times negative is a positive. So we get 0.692 plus the product of these two values here. And our denominator is still going to be negative because this is larger. It's 0.42886. And then we just carry out the work here. We square the negative 0.446, which becomes positive. And then we square the 0.590. We complete this and we get a value of 0.593. So this is the partial correlation between depression and self-esteem. It's negative 0.593. And if we go up here, it was originally minus 0.692, right? Minus 0.692, same as here and here. So these are symmetrical. So whatever you have here, you'll see above the diagonal, right? So we reduced it a little bit, but not a lot. So perceived physical appearance did account for some of the correlation between the two, but it wasn't everything. So this, I believe, is from what I had earlier. I deleted something, you recall. Let me undelete that. Hold on, Control Z. There it is. Using the correlation. Oh, good. So yes, there's a data set. I'm going to actually include this for you so you can try it on your own, or try to replicate what I did on your own as well. So I'll give you that data set and see if you can actually replicate what I did here. It's basically you doing what we did in when we worked with a variance, where we use Excel in order to calculate everything that we need, like we need a product X by Y, etc. Okay. All right, using well, I'm going to show you an example right now. So using the data, using the following table, calculate the zero-order Pearson correlation between self-esteem and perceived physical appearance. Okay, all right. The zero order. So zero-order correlation means you're not controlling for anything. Okay, so we need calculate the zero-order Pearson correlation between self-esteem and perceived physical appearance. So what I did was I just used Excel. I'll bring this in here. So I had self-esteem, perceived physical appearance. So I need their correlation. So there's a lot of things I need here. Like for one, I need the product, the X times Y. If we let self-esteem equals X and perceived physical appearance equal Y, I'd have to have their product, right? I also need self-esteem squared, and I need perceived physical appearance squared, because that's what my equation requires from me. So let's take a look at this. So here's the equation. So we have the summation of X times Y. So I need an X times Y. I have the summation of X times the summation of Y. That means I need a summation of X and I need a summation of Y and their product. And then I need a summation of X squared. So I need I need an X squared, and then I also need a Y squared. So if I have all of those, I can go ahead and complete my work. So I used Excel and I built myself I built myself this structure, right? So I had self-esteem, perceived physical appearance. I need the product. So 5 times 4 is 20. I need the individual value. So that's 5 squared is 25 and 4 squared is 16. If you recall that to do that, the product, I just put in what was in cell C2 and multiplied it by what was in cell C4. So it's a C2 times D2. Remember, I did that. And for the squaring, this time I did something a little bit different. I think I showed this to you before. I took C2 and I used that upper little, what do you call that little V that's pointing upwards? Upside down V, right? I don't know, it's a little symbol which indicates squared, and indicates that I'm going to use a power, and then I hit the power of 2 there to see C2. Then I hit enter, right? And that gave me that. And then of course I could just drag things down and get everything I need. Right, and I need sums, so I just use the sum function, right, in order to summate everything. So once I had all that, I could come back here and enter everything into my equation. So the sum of X times Y was 381. The sum of the X's was 78. The sum of the Y's was 72. And I had 15 values here. And then the sum of the X squared is 414. The sum of the Y squared is 358. The sum of the X's squared is 6084. The sum of the Y squared was 5184. So I did that and just work out this problem. I get a correlation of 0.647. There you go, 0.647. That's a pretty strong correlation. Using the correlations in the SPSS output below, calculate the partial correlation between body mass index and PPA controlling for self-esteem. So here we have body mass index. This is basically what we did before. Body mass index, but just different data set. So, actually, no, it's not what we did before. I forgot what we controlled for last time. I was pretty sure. Oh, we're doing body mass index. Oh, so we were just doing the reverse of what we did before. Body mass index and PPA before we did body mass index and self-esteem, right? And now we're doing body mass index and PPA. So I would think the higher one's body mass index, that would probably affect one's perceived physical appearance, depending if one's a male or female. Sometimes males tend to think that they're better if they're stronger and bigger. It depends. So this would be an interesting one to compare the correlation between male and female. But we're just doing this for doing the calculation right now. So I have my variables and their correlations. Okay, so here we go. Let's go do the work. So the correlation between what did I say, between body mass index and PPA. All right, so A is BMI, B is PPA, and C is self-esteem, right? Okay, right. So the correlation between A and B, between BMI and PPA, is negative 0.173. So it's not a big correlation. So it's kind of like a small correlation, actually. That's good news, right? Perceived physical appearance isn't so strongly tied to BMI. And then we have the correlation between BMI and PPA. PPA and BMI and self-esteem, and then PPA and self-esteem. That one's a little bit stronger. So we do those, and then again in the bottom we work with those squaring the correlation of subtract. So this is kind of the reverse of the R squared, right? So it's 1 minus that, because the R squared has to equal 1 maximum. It can be 1, the amount of shared variance. So we're going to find out how much variance is not shared among the variables, right? We take the square root of that. We got negative 0.153, negative 0.153. So let's compare that to BMI and PPA. So we got negative 0.153, but BMI and PPA, if we just look at them here, it's minus 0.173, BMI and PPA. And what did we find it to be? BMI and PPA was, didn't change that much. Went down to 0.153 from 0.173. So again, controlling for self-esteem didn't really do that much here. But that's just how you would do it if you were doing a partial correlation. All right. Next question was, given the means and standard deviations for BMI and self-esteem, means and standard deviation and their covariance, calculate the Pearson correlation. So my guess is that you were listening very closely to me and you knew that I showed you what the equation was for a correlation. Up here, I said correlation is the quotient, covariance xy divided by standard deviation of x and standard deviation of y. You're going to say, oh, this is easy. So I'm just going to take this information that I was given, the covariance, and divide it by the 2 standard deviations, and I am done, right? That's exactly what we did here. We took the covariance between the 2 variables and divided it by the product of the 2 standard deviations, and I get a correlation of 0.136, negative 0.136. Again, so all you need to do there is, if you have the covariance and you have the standard deviations, you're done. You've standardized the covariance, and you've got your correlation. All right. So correlations are not horrible, but they're important. We use them, and just a couple points about them. We use them because they provide us with some information about how 2 variables are related. However, you don't want to use them to make any kind of determinations. Correlations can imply possible causation, but that's all they can do. causation is much more complicated than that. We don't really cover it in this course, except for to say that you have to do studies over and over again and find relations that are exactly the same before you can determine causation. But there's many, many more things involved in that, including experiments and time precedence. There's a whole bunch of stuff. But when you see two things are related, it should open questions. A better way to make predictions and to start getting closer and closer to even implying causation is to do a regression analysis. So a regression analysis is a step above a correlation, because now we're actually allowing for there to be error in our prediction. Correlations don't really have any error. They sort of do when we talk about the proportion variance. You could say that proportion that was is shared and that's not shared. So that's kind of starting to point towards some error in our judgment, but this is much more formalized when we deal with correlations. But let's start with talking about different kind of correlations. We're only dealing with a couple here. We don't deal with regressions that are related to non-parametric data. It is covered in the book if you're interested in it. We don't cover it in this course. It's something called logistic regression. But linear regression can be either simple or multiple. So simple regression, you have one predictor variable and one outcome variable. Multiple regression, you have one outcome variable and multiple predictor variables. This is the prediction equation. Predictions themselves don't have errors. This is just the prediction. You'll see what I mean shortly, or a little bit later in this lecture. So this is just a prediction. A prediction itself doesn't have an error until it's compared to the actual value. Then you get an error. You get a residual. So this is the prediction equation. Notice I have a little hat here on top of my y. Let y be my outcome variable. Y sub I is an individual score on my outcome variable. Let's say I'm trying to predict Piper's score on happiness. From Piper's score on how much what do you call it? Nectar he drinks. Piper's my parrot. How much nectar he drinks every day. So this is your equation. It's a line, right? You have an intercept. The b sub 0 is the intercept. B sub 0 because we want to differentiate it from any predictor variable. The subscripts here represent the relation between the variable and its predictor. The b sub 1, when it's attached to predictor variable x sub 1, is a slope. So you have your intercept and your slope in this line. Notice also that there's an I behind the x and there's an I behind the y. So this means this is an individual's outcome. This is an individual's prediction. This is the predicted outcome for the individual, and this is the individual score on the predictor variable, or whatever the variable I'm using is. So I'm trying to predict something from something else, basically. Multiple regression, you'll notice we have more than one of these variables. So I have b sub 1, x sub 1, I, b sub 2, x sub 2, I, going all the way to k, where there's k different predictor variables. So you can see there's one, I equals 1, whatever, the different i's, and then going up to k. I should have probably written this as I equals 1, 2, etc. You'll notice here, though, that the b's don't have any i's. Poor bees, they're blind. They can't see. Well, they should, hopefully they can see because they're trying to get a pollen from the plants. But these bees don't have eyes. So that means they do not vary by individual. They're the same for everybody. They remain constant for everybody. Well, of course, the variables themselves vary if they're variables. We can, in simple regression, multiple regression would be much more complicated than this. But in simple regression, we can calculate the slope, like the B1 here, from the correlation between the variable y and x by taking the correlation and multiplying it by the ratio of the standard deviation for the outcome variable y by the standard deviation of the outcome of the predictor variable x. So we tend to just call outcome y and the predictor x. It's kind of just by convention. We can use this information to calculate to write our regression equation. And this is actually important because we use these regression equations to make predictions. Like if I wanted to predict how many something units of something I'm going to sell based on, I don't know, customer preference or something like that, I can make a prediction and therefore work on improving customer preferences or customer liking or something like that. So I can actually make predictions and then use that to inform some kind of policy decision, right? So if I take this prediction equation, now notice that I changed the b sub 0 to an a and the b sub 1, I just let it be. I let it be b. Lots of fun stuff when you talk. So probably should have an x sub I over there. X sub I. Hey, come on. There you go. So let me just fix that real quick. Where am I? Where am I? X sub I. Equation. Here it is. X sub I. Oh, come on. There you go. So slow. There you go. So I just want to make sure it's all right. So if I rearrange this equation, I can solve for the intercept. I have the slope and I just need the intercept. But notice that instead of each individual's score, I substitute the mean of y for the y prediction, right? And the mean of x for the x variable. The reason I do that is because absent any other information, the mean is always the best estimate of a value, right? So there you go. So let's do one. Exercise, write the regression equation for the following data with per capita cigarette consumption in 1930. That's our x variable. Predicting incidence, new cases, incidence means new cases, of lung cancer per 100,000. So lung cancer is per 100,000, right? That's your y variable. Also interpret the effect. So the mean cigarettes smoked is 603.640 in 1930. Wow. Per capita, that's per person. People used to smoke a lot in the old days. Mean lung cancer cases were 20.55 per 100,000. Here's our standard deviations, and here's our correlation. So that's a pretty strong correlation. Cigarettes consumed and lung cancer, right? So it was a big correlation. So we can do that. So calculate the slope first. We do b equals r, standard deviation of y divided by standard deviation of x. So the r was 0.737. The standard deviation of y was 11.725. So those are cases per 100,000. That's per 100,000 people. And then the standard deviation for cigarettes consumed, and I get 0.0228. That's my slope. Using the equation I showed above, I can find my intercept by subtracting b times the mean of my predictor variable, cigarettes consumed, and subtracting it from my mean of my outcome variable, cancer cases. So I get 20.55 minus 0.0228 times 60364, and I get 6.787. That's my intercept. So now I can write my equation. A plus bx. So A is 6.787 plus 0.0228 x. That's x is cigarettes, right? All right. That's per country in this. We're not doing these are individual countries. So there's 2, 4, 6, 8, 10, 11 countries, right? So let's look at how, with regression, the most important thing is how you interpret everything. And this is what's going to be important for you as we move forward. So each additional cigarette smoked per person in 1930, right? Because that's my x variable. Again, each additional, because we're talking about per capita cigarette smoke, per capita is head, right? Per person. Each additional cigarette smoked per person in 1930 was associated with a 0.0228 increase in the incidence of lung cancer per 100,000 people. So the slope reflects the change in the y variable for each unit increase in the x variable. So the change in the outcome variable for each unit increase in the predictor variable, and everything is scale dependent. Cigarettes is different than incidence. Incidence is is a person, right? Cigarettes is a cigarette. So each cigarette increase, that's wild, huh? That's a big effect. Doesn't seem like a big effect when you're talking about each one cigarette smoked. Right? If this was negative, it would be a decrease. This is positive, so it's an increase. Okay. All right, let's go talk more about regression. So remember, you need to know how to do that for the exams. Regression assumptions. First of all, we assume that the relation is linear. You can have curvilinear relations in regression, but then you have to do a little extra modeling. Say if I believe that the effect of cigarette smoking on lung cancer cases per capita was not linear, and it looks something like an inverted U, upside down U. So it's like an increase followed by a decrease. What I would do is I take my predictor variable, in this case, cigarettes per capita, and then add a term where it'd be cigarettes per capita squared. If I thought it was cubic going up and down, I would do to the third power. I could do a lot of different things too, but linear regression, that's not linear regression anymore. That's a more complicated model. But linear regression assumes linearity. Second is the observations are independent. So my observations are in no way related to yours. We're two different independent individuals. We're not like brothers and sisters or whatever. Once you introduce connections, you add more confounding variables, and you have to control for those. There's normality at each level of X. So X is my predictor variable, right? And there's levels of it. Like say cigarette smoke, there's different levels, 1, 2, 3, 4, 5. So we're assuming across the different levels of my predictor variable, right? We have normality. What we have normality in is the leftover stuff, the residual, right? So when you say this is the distribution of my outcome variable, Y, in this case was per capita, it was lung cancer cases per 100,000. Well, I'm not looking, this is going to be kind of interesting, and I apologize for sounding complicated here. I'm going to try my best to explain this. When we make a prediction, there's always leftover. We can't make perfect predictions. If I have one variable predicting lung cancer cases per 100,000, cigarette smoking is an important predictor. It may account for it accounted for a lot of the variation. We saw that the correlation was 0.7. R square, 0.7 squared is about 0.49. So almost 50% of the variation in my outcome variable, lung cancer, was accounted for by cigarette smoking. But we want to account for 100% of the variation, right? So 50% of the variation is left unaccounted for. Well, that unaccounted for stuff has its own distribution. And that's what we're plotting here, because we can't plot Y anymore, because Y doesn't exist anymore once I make the prediction. Y has been taken up by my predictor, and all that's left over is the residual. So we're looking at the variation. We've accounted for 50% of the variation. The remaining variation is left over, and we're looking at the distribution in that remaining variation, and that's what we're looking at here. And that is assumed to be normal at different levels of my predictor variable. So there's cigarettes can be 1, 2, 3, going up to hundreds per year. And we have equal variability at every level of X. So this variance, so sigma here is a standard deviation, our variance would be sigma squared. So basically this should be equal going across. So that's what we're looking for. That's something called homoscedasticity, homogeneity of variance, if you will, across the different levels. That's pretty awesome. So I talked about how to, we talked about how to interpret the effect of a predictor on an outcome just a moment ago when I gave you that example. If that's with one predictor variable and one outcome variable. When I have more than one predictor variable, we still focus on just one predictor at a time, right? Like let's say, in addition to cigarette smoked, I looked at pollution in well, we're looking at countries, so what's the pollution rating? So some countries have more pollution than others, right? That would be a separate variable, right? But when I'm looking at the effect of cigarette smoking on my outcome, I'm holding pollution constant. That means I'm assigning the same level of pollution to everybody, so that really pollution doesn't do anything in those equations when I'm looking at the effect of cigarette smoking. If I decide to look at the effect of pollution, I hold cigarette smoking constant. Like I give everybody the mean level of cigarette smoking. So I always hold one thing constant. So whenever I'm doing multiple regression, when I talk the effect of a predictor and an outcome, I'll write each unit increase in X, whatever my variable is, results in a whatever my slope is, a B change in the outcome, and then I'll add holding all other variables constant. So if there's only one other variable, you can name the variable. But if you have 3 or 4 other variables, just say holding all other variables constant. So you want to add that. When we do regressions, there will be outliers. Outliers are variables that they're just very, very different, right? So like, let's say I'm trying to predict obesity from hours of exercise. And I'm looking at my outcome variable obesity and say, there's most people are within a certain range, weight, in a certain range, but there's some people who are morbidly obese. Those individuals would be outliers. Outliers can have an impact on the results of your analysis. An outlier, again, is an extreme case. If you recall, when we plotted the mean, if some values are extremely large, they're going to have a pull on the distribution. They'll skew the distribution. So we want to look for outliers, and we have to decide what we're going to do with the outlier. So we stick this under regression diagnostics. So again, here's our regression equation. This is a multiple regression equation. We have our outcome variable. Notice that I don't have a hat here now, right? He must have been really hot, so he took off his hat. So this is actually an observed value of my outcome. These are my slopes, and these are my predictor variables. But now I have E sub I, so that's my residual. That's the thing that we were looking at here, right? The residuals, the leftover. When I have the hat, there is no residual because that's a prediction. The prediction doesn't have an error until we compare it to our observed outcome. The residual, the leftover, is the difference between the observed outcome and the predicted value, right? That's the residual. If we have residuals that are greater than 3 standard deviations from the mean, so the mean, residuals are assumed to be normally distributed, standard normal distribution, mean of 0, a standard deviation of 1. If we have residuals that are like out here, way out here in this distribution, 3 standard deviations from the mean seems to be what we generally use. We consider those outliers. So we look for outliers. Doesn't mean we're going to get rid of them. We just look for them, and then we decide what we want to do. We may say, I have 174,000 people. I can get rid of the outliers. It's not going to affect my results at all. I look at the difference in my results with or without the outlier in it. I can also say, well, I have only 5 people, 10 people in my sample. If I get rid of an outlier, I'm going to drastically affect my results. So you have to make a decision whether or not you want to eliminate outliers, given how expensive it is to collect data, how time consuming it is. You may or may not want to delete it. So you should always investigate them and see what their problem is. Sometimes the outliers are just data entry errors. Like instead of 61, I put 661 in. It was too quick in my typing, or something went wrong. Although the way things are done now, you probably don't have to type so much, so we probably eliminate a lot of errors. That's really good. So we have to check for that, and we have to make decisions about that. So if you saw this, I hurt myself this weekend while I was cycling. It was a Friday, and this hurricane was coming up the East Coast and just dumped a lot of rain everywhere. I was cycling Friday morning. I was so happy. I was going fast and enjoying myself. And I hit this corner and I said, oh no, I got to slow down. So I put my brakes on and was making a turn simultaneously. And there was all these wet leaves because the leaves are falling, all these wet leaves that have just rained the night. My bike just went out from under me. Thankfully, I remember from this skiing coach I have, who's also a triathlete. He says, when you crash cycling, kind of get in a little ball, almost like, hold onto your handlebars and take the fall. And it actually works because I scratched myself really bad. You have a road rash, as they call it, so it's still healing. And then on my knee, but only those two places. Had I put my hands out, I probably would have broken something. So anyway, that's why I'm playing around with my arm. Had so many bandages on me for the last few days. All right, continue with the regression diagnostics. We also look for something known as multicollinearity. One thing we don't want is we don't want our predictor variables to be highly correlated with one another. We'd like them to be different. We'd like each predictor variable to account for some, we talked about the R squared, we wanted to account for some of the variability in the outcome. We don't want them to have too much overlap. That'll mess up our equation. Ideally, our predictor variables would be uncorrelated with one another, but they'd be correlated with the outcome variable, so that pull some of that variability, that explains some of that variability in the dependent variable. So that's what we'd like to happen. All right, so we check for multicollinearity. The greater the correlation among the predictor variables, the worse. Right? Tolerance is the proportion of the variance of a predictor variable not accounted for by the other predictor variables. We'd like the tolerance to be larger. So it's essentially, we do regression analysis among the predictors. And we're hoping that the other predictors do not account for a great deal of variance in one another, right? So tolerance, again, we're going to calculate that as a portion of variance of a predictor variable not accounted for by the other predictors. Larger values are better. And then there's another measure, the variance inflation factor, which is just 1 divided by the tolerance. So you have these two. So tolerance values less than 0.1 are troubling, right? And VIF values greater than 10 are worrying. Okay. Remember, so the value less than 0.1 would mean most of the shared variance is accounted for by the other variables. Right? Larger value means less is accounted for by the other variables. We also want to check for, well, what happens if we find variables that are strongly correlated? They might be measuring the same thing, so we can get rid of some of them. The ones that are highly correlated. We check for homoscedasticity. I'd mentioned that we want our variance of our residuals to be the same. We don't want them to be different. So we're going to take a look at that using plots. And then we'd also get the correlation of determination. So we'll have similar statistics that we have for correlations. So your job is to read the text. Make sure you look at the figures that I provided in the text that explain all of these things, and get ready for the exam. In the exam for regression, I want you to be able to write the regression equation, simple regression equation, and I also want you to be able to interpret regressions, and then do maybe some minor diagnostics. Okay? All right, thank you very much. This was wonderful as usual. Have a great day.